Okay, I'm going to show you Bernoulli right now with this sheet of paper. Okay, basically you can do this at home. Take a sheet of paper like this, a strip of paper. Let me make it a better strip, a little neater strip. We'll probably do this in class tomorrow. Take this, then blow over the top of the paper. See how it goes straight? Blowing over the top of it, less pressure up here, more pressure down below it. Nothing more to it than that. All right, now the mathematics of it, the physics behind it is a little tricky. Excuse me. The physics behind it is a little bit tricky, but it's really nothing. It's not a big deal because it's just conservation of energy, and it's actually conservation of a non-conservative force is what's going on here. All right, so let's take a look. So here we go. Conservation. So the work done by a non-conservative force is the change in pressure times the volume. Okay, because that's equal to force times distance. So the work is equal to the change in pressure times the volume. So 1/2 mg squared plus mgy minus 1/2 mv2 squared plus mgy2. Okay, you've done this before. This is like a block sliding down a hill with friction on it. So the work done by friction is equal to this. Okay, but now we're just replacing it with pressures, and we come up with Bernoulli's equation, which basically says in a steady flow of a non-viscous incompressible fluid, the pressure, the fluid speed, and the elevation at 2 points are related by this equation. Now, how do we work it? How does it look? That's all fine and good. Here's some examples. The truck is stationary. The tarpaulin is nice and flat. The truck starts moving. Account for this behavior. Fast moving air on top, slow moving air on the bottom. This is how you can see leaves kind of in the back of a pickup truck or something like that, where they're hauling leaves, or maybe there's just some leaves in the back of there, or a napkin or something from a workman, and the wind it kind of rises up above the bed of the truck, and then it flies back once it catches the wind. Okay, and comes zipping past you, but it floats up out of there because fast moving air here, the truck here, the slow moving air, the higher pressure down here with the slow moving air, and boom. On a wing, same thing. Faster air there produces a small lifting force. This is why this is this. Now, the way a plane actually takes off is thrust from the propeller, an angle of attack of the wings for lift, and also once they're cruising along, the Bernoulli helps the faster air over the top, slower air coming across the bottom. This has been disputed in highfalutin physics a bunch of times, but the general idea is there. Okay, so what does this look like? Well, let's go look at your hamster problem. Okay, is that it on this? Okay, here's all your things in the house. All right, I'll talk about the curve. Oh, I love this. Okay, without spin, a ball just moves through the air and doesn't curve at all. But what this does, when you get this curve of the ball, this is called the Magnus force. Okay, you get slower moving air on this side. Okay, and then faster moving air on this side, so that the pressure is reduced, so you actually get a curved ball, which works pretty slick. Okay. Okay. Efflux speed. Now this is kind of interesting. Notice, if I turn this pipe around, it just go up to the same height. And if I left this continual, and as this goes down, this will get smaller and smaller and get slower and slower until it'll go down to nothing when it's even. Okay. Pretty cool. If I can leave this at a steady state, I'd just have a nice little fountain. If I was pouring water in here, I just have a nice little fountain up at the same height. And the velocity of this, believe it or not, the velocity of this is good old square root 2gh, square root of 2gh. All right, so now what does the Bernoulli equation look like? Okay, what does the Bernoulli equation actually look like? So this is how you use it. This is how you use Bernoulli, all right? And then we will look at your, we'll look at a couple homework problems from this. I've got one other homework problem I've got in the hopper there too. Okay, so it says this, that the pressure on one thing, on one object in a system, plus 1/2 the density of the air or water, 1/2 V1 squared. Boy, doesn't that look like 1/2 mv squared? You got it. It's the same thing. Plus rho GH. Wow. See, these are all analogous to kinetic. This is the kinetic energy of the fluid. This is the gravitational potential energy of the fluid, is equal to P2 plus 1/2 rho 2 V2 squared plus rho GH2. All right? And then the way we do it is we want the change. We want P1 minus P2 is equal to the change in pressure, which is, and then we move, so we take P1 minus P2, we move that to this side, and then we put all this other stuff on the other side. So then we've got 1/2 rho, and we're assuming that rho 1 is equal to rho 2, okay? 1/2 rho V2 squared minus V1 squared plus rho G times H2 minus H1. And this is how we use it, okay? And we also remember, for like the lifting wing, for the wing, where do you get that force? Where's the lifting force? The wing lifting force then is this. Change in P is equal to F over A, which this is the area of the wing, is equal to, now we're not going to worry about the change in height. We're going to say that H2 is equal to H1. All right. I mean, it's compared to the speeds that we're going and that, you know, those like foot difference or something like that at the most, few inches difference, but it doesn't matter. So H2 is equal to H1 is equal to 1/2 rho V2 squared minus V1 squared. Okay, that's how the wing lifting force works. All right, so let me show you some of the homework problems then. I think we've covered everything, and so now we can just go look at straight homework problems, okay?